in order to show idempotency of the Young operators, so property 1, let's just take the square of some Young operator. So E lambda p squared. What's that? Well, E lambda is just S lambda, E lambda p is S lambda p, A lambda p, and then we repeat this, S lambda p, A lambda p. And if we look at this term here in the middle, that's just a bunch, linear combination of permutations. So the whole thing is a linear combination of terms that look like this. S lambda p, some permutation q, and then A lambda p. Yeah, q a permutation. Okay, and now we have to show that all these terms are proportional to E lambda. They look very similar to what the E lambda looks. So this was our E lambda or E lambda p, the structure of the Young operator, the symmetrizers on the left and the anti-symmetrizers on the right. And now what we do with this Q here is we introduce some additional permutation here in the middle. So we cross some lines here in the middle in general. Okay, we also know that if Q is the identity, then the whole thing is not zero, because that's just the Young operator, and we know if we expand this, there is this term proportional to the identity, and then lots of other terms, and the coefficient of the identity, for example, is non-zero. It's just 1 actually. Okay, so we know that the lines here are connected in a non-zero way. So, for example, all these lines leaving the first symmetrizer, they are connected to different anti-symmetrizers, like this. And that's possible, of course, because the length of the first row tells us how many lines enter here, but it also tells us how many anti-symmetrizers we have here. Because the length of the first row is the number of columns in our diagram. Okay, and then here the second symmetrizer also connects to all anti-symmetrizers that still have something to connect to, so not like this one down here, which is already used up, and so on. So there is some non-zero connection here for the Young operator itself. Now, what happens when we do this extra permutation Q here? This extra permutation could, for example, take two lines that connect to the same symmetrizer and just exchange them. Well, but we can always undo this by just exchanging lines entering a symmetrizer at no cost. So if this Q just permutes lines entering the same symmetrizers, then we still get E lambda p. If the Q permutes two lines that enter the same anti-symmetrizer, for example, this one and this one, then we can undo this by swapping two lines here. That gives us a minus sign. So we can get minus E lambda p. Or if we have a more complicated permutation here, not just two lines involved, but only lines entering the same anti-symmetrizer, then we can have plus or minus E lambda p here. But still proportional to E lambda p. That's the point. Now, what happens if we take, say, this line and swap these? So lines that are connected to different anti-symmetrizers and to different symmetrizers. So then we change how the symmetrizers and anti-symmetrizers are connected, and if we swap these, then we automatically have the situation that now two lines from one symmetrizer are connected to the same antisymmetrizer, and then it's 0. So whatever we do, can also combine these somehow, but whenever we do the last thing here, we get 0, and for all the other cases we get something that's proportional to E lambda. So that's almost idempotency. We have some factor here now, but we have to show that it's non-zero. So we see E lambda p squared is, let's say, some number, eta lambda, E lambda p. But we still have to show that it's non-zero, this number. So if this number was 0, then the thing would be nilpotent. It would square to 0. But then the trace of the following map which map? Just right multiplication with E lambda. So we take some group algebra element Q and map it to Q times E lambda P. The trace of this thing here would be 0 if the thing was nilpotent. But we know the trace of this, because the trace of this, that's just the coefficient. Well, it's determined by the coefficient of the identity of this term here on the right. And we know that the coefficient of the identity is 1, so this is not 0. So we showed this. E lambda p is identity plus terms that are proportional to other permutations. And since we have something non-zero here in front of this, the trace is not 0, so the thing is not nilpotent, so the eta lambda cannot be 0. This means the Young operators are really essentially idempotent.